Hi, everybody. I'm Lisa Lippincott, and I'm here to talk about the Principia Mathematica and the foundations of arithmetic in C++. Now, you might think I'm being rather bold by titling my talk in Latin, and I'll cop to that. You might think I'm being extremely bold by titling my talk after Isaac Newton's Principia Mathematica, Mathematical Principles of Natural Philosophy. I am not. I am in fact titling my talk after Alfred North Whitehead and Bertrand Russell's Principia Mathematica, which is bold enough they titled their book after Newton's. Caused a little bit of a scandal, as I understand it. And I'm doing this because I think of this talk as taking the place for C++ that the Principia Mathematica takes for mathematics. The Principia is a book, it's 3 volumes, that in exacting detail builds up the basics of mathematics from the principles of logic alone. That idea that mathematics is based on logic was new back then. It had only been around for a fairly short time. And this was the real demonstration that it could be done. So the Principia is written in a rather dense fashion with a lot of formal notation. It's quite difficult to read. Until Bertrand Russell met Kurt Gödel, he was convinced that no one had ever read the entire Principia. But Gödel convinced him that he had read it. So it is one of the great books of English literature that no one wants to read. So this is a sample page. This is not a random sample page. This is page 86 of volume 2. It's a famous page of the Principia because this is the page on which they prove that 1 + 1 is equal to 2. A proposition that they find occasionally useful. So the Principia has a ton of material. It's in very dense detail, a lot of formal notation, and I'm going to try and do the same thing in 90 minutes. I'm going to use a number of tricks to do that. I'm going to talk very quickly and take questions at the end. Sorry, Dave, if you're out there. I am going to summarize a lot, and I do have an advantage over Russell and Whitehead. I have 100 years of mathematical hindsight that was not available to them. Particularly the development of type theory. Types were a new idea when the Principia was published. Bertrand Russell had invented the idea of type only a handful of years before, and the Principia, as far as I know, was the first major outing for the first major use of the idea of type. So if you're a person who likes types and who doesn't like types, you can thank Bertrand Russell. I do have one more advantage, and that leads us to the second part of the title, the foundations of arithmetic in C++. Because English is not a formal language, this can be read in 2 different ways. I could be talking about the foundations of the way C++ does arithmetic, and I could be talking about the foundations of arithmetic expressed in C++. I'm going to do both. I'm going to talk about how C++ does integer arithmetic, and I'm going to describe it using C++ lightly modified as my formal language. And that is a great advantage. C++ is a far better formal language for actual use than anyone had 100 years ago. In fact, I would say it's a far better language for actual use by people of expressing complicated things than most mathematicians use today. So I'm not going to do exactly C++, I'm going to add a little to it. And the principal addition I'm going to use is the idea of function interface. This is a function interface. It's a block of code divided into two parts by this implementation statement. And the idea is that when we call a function, the caller is responsible for everything that happens before the implementation statement. And then the function implementation is responsible for everything that happens after the implementation statement. So preconditions go above the implementation statement, postconditions go below the implementation statement. And we are going to try and write function interfaces for every one of these integer operations. Let's begin. There are three basic things to know about any function. We need to know how it interacts with the three basic ideas of procedural logic. And in my opinion, the three basic ideas are stability. Over certain periods, the state of an object will be stable, and therefore the object will hold the same value. Substitutability. There are certain points in a program where two different objects hold the same value. They are interchangeable for each other. And finally, repeatability. If we perform an operation a second time, and we do it in a way that is sufficiently similar to the first time, then we are repeating the operation. And when we repeat the operation, we get sufficiently similar results. So those are our three principles: stability, substitutability, repeatability, and every function interacts with these three principles. For stability, a function might end a period of stability for an object. It might begin a period of stability for an object. It might also only be callable during a period of stability for an object. So we are going to specify those things in our interfaces. For substitutability, a function might have a precondition of substitutability or a postcondition of substitutability. And finally, for repeatability, our interfaces need to explain what it means to repeat the function. And I'm going to introduce the term discernible input. If you repeat the discernible input to a function, then you are repeating the function call. And what do you get out of that? If the function call is repeated, then you will get the same discernible output. So each operation, we will specify what the discernible input is and what the discernible output is, and we will know that if we call the function again with like discernible input, we will get like discernible output. So let's take a look at our list and see how it interacts with stability. For each of the parameters highlighted here, the operation consumes the right of stability that the caller gives it. That is, the caller of this operation has to have a right to expect stability of this object. It transfers that right away. It gives up the stability of the object, and thus, from the caller's point of view, the object may change. After the function, these same operations transfer out a new right of stability to those same objects. That is, this is a new right of stability. It's stability in a possibly different state. So for these parameters, the operation is ending a period of stability and starting a new period of stability. For all of the others, the function requires an immunity from instability. The caller needs to guarantee that these parameters will remain stable for the duration of the operation. So every parameter here is either a write-in and a write-out, or it's an immunity that covers the entire duration of the operation. The blue ones we can only call the operations when the blue operands are in the middle of a period of stability. There is one more bit of stability, which is these operations return a result. These operations provide a right of stability that is new to the result object. So, and that's all there is for stability. Substitutability has a fair number of things on the low end that look alike. In each of these cases, the operation returns a reference, and the reference is to one of the operands. It's aliased. Aliasing is a kind of substitutability. It's substitutability of address. So in each of these cases, there is a postcondition that the result is aliased to a parameter, and usually the left-hand parameter, and that's always a postcondition for these operations. The rest of the operations, of course, returned a right to the result. These operations don't return a separate right to the result because they are also returning right to the parameter. Only one right comes out of them. There's a little more substitutability. For these operations, there's also a postcondition about the value of the object that involves substitutability. After an assignment, the two objects will be substitutable for each other. They will have the same value. The same is true after a comparison operation if the comparison returns true, if the equality comparison returns true. If it's a not equals comparison, you get substitutability if the result is false. Here, I'm doing something I don't like to do. This is a code smell here. Any interface that has an if statement in it is a code smell. This is saying that you don't really know the full postconditions of this operation until you branch on the result. This isn't very nice. This complicates the logic of every caller to the operation. In this particular case, I think it's okay because almost all uses of double equal or bang equal are going to be followed by a branch on the result of the comparison. So I'm not too worried about this particular one, but these two branches are the only branches I'm going to put into the interfaces of the arithmetic functions today. I'm going to avoid branches everywhere else. Okay, that's substitutability. I should say there will be more substitutability, but in most cases, we're just going to get substitutability through the back door by claiming that things are equal. What about repeatability? It's fairly simple for these operations. In general, the parameters form the discernible input to the operation. If the values of the parameters are the same, then we are repeating the operation. There's one exception when we do a simple assignment. The value of the left-hand parameter isn't part of the discernible input. The left-hand parameter need not even have a value when we do an assignment. The discernible output is also fairly simple. The result of the value of the result of the operation is always the discernible output. except for these two operations down in the corner. These two have some extra discernible output, which is the value of A. So there are two parts to the output for A++ or A-. And with that, we are done with the basics, and we can in fact show the entire interface for assigning an int to an int. In the prologue, the caller gives up the right to the stability of the parameter A. The caller extends an immunity from instability for the parameter B, and that immunity needs to last for the entire duration of the operation. The value of B is the discernible input. If we repeat the value of B, we are repeating the assignment. And we have the implementation statement. The rest is the implementations problem. After the implementation, the result, the address of the result, and the address of A have to be substitutable. They're aliased. The function produces a right to the stability of the result, which, because it is alias to A, is also the right to the stability of A. There is only one right, despite the fact that there are two expressions that we can use to get at that right. The result is the discernible output. If we repeat the assignment, we will get the same result. And finally, the result is the value of the result is substitutable for the value of B. That's the interface for assignment. But I cheated. This is the interface for assignment of an int to an int. I promised to do all of integral math, and we have a lot of integral types in C++. These are the standard integral types. We also envision that implementations may add to the list, and we could have a great many extended integral types. So we're going to have to deal with all of them, and of course we will generally deal with them in bulk because that's the way to get through the lecture. There are two things to know about an integral type. Is it unsigned or signed, and what is its width measured in bits? These two facts tell you essentially everything you need to know about how the integral type works. And I'm going to combine these two facts into a handy structure. So the structure has a Boolean, is it signed, and it has a width, which is expressed as a bit size t, which is, of course, a new type. I'm going to say bit size t, at least for our purposes today, is not a C++ integral type. It's its own thing. It doesn't obey all of the C++ integral type rules. So think of it as a type with units. Measuring things in bits, some non-negative number of bits. It's how wide is an integer. What do we do with an integer kind? Well, the main thing we do is compare them. There's a partial ordering on integer kinds. And you might think of this as, does one integer kind fit within another, a containment ordering? Containment in multiple dimensions, generally a partial ordering. But you shouldn't think of it that way. Don't think of this as containment. It messes up your type theory. Instead, think of this as the requires clause on this function convert. When one integer kind is greater than or equal to another, there is a special function that we will call convert that takes us from the smaller kind to the larger kind. So here convert is the nice conversion operation. And this is how we are going to tie the types together. We have many integral types. They come in pairs, signed and unsigned, except for the with 0 type. And the arrows represent conversion functions. They take us from one type to another. These are the nice conversions. And the nice conversions help us explain why we sometimes think of the same value as being in more than one type. This, type theoretically, is nonsense. The same value can't be in more than one type. A value has one type. So if we are being good, we should have put subscripts on these values. 5 in this unsigned type is different from 5 in that signed type. They are different values, but we gave them the same name. Why did we give them the same name? We think of them as a lot alike because the conversions bring them together. So we generally name the numbers the same, and when the nice conversions bring them together. Now, of course, there is some biggest integral type, and it doesn't quite make sense to say that 5 in this integral type, unsigned type, is the same as 5 in that. There's no integral conversions that bring them together. But we imagine the sequence of types going on and coming to a colimit off on the horizon. And the conversion to this colimit, to this type z that is off on the horizon, takes these two numbers together, and so we consider them like numbers. They are not exactly the same value. They are different values because they're in different types. But we consider them pretty much alike because they go to the same place in the colimit. So that's convert. Convert has a strong type requirement. All of the values of the type must be convertible. It's a total function, and it is the nice conversion function. I'm giving it the nice name. We also have some less nice conversion functions, which are for going against the grain. Ordinary convert is showing us what the grain is. The other conversions can go against the grain. And the basic one I'm going to call convert narrowing. Convert narrowing has a strong precondition because it's a partial function. You have to match certain conditions in order to have legitimate parameters to convert narrowing. But convert narrowing lets us lift to a type that's higher, that is higher up in our diagram. There's one more that we will see today, which is convert modular, which has a weak postcondition. You can convert modular any value, but it does have a weakened postcondition, and which is that only the low bits of the value are going to be right after you do convert modular. With, of course, the low bits, what's low bits being determined by the type you're going to. Modular arithmetic is a fine field of mathematics. It is not very well served by the C++ integral types. And in fact, for today's purposes, anywhere you see convert modular, you can think of it as it's like convert narrowing, except instead of having a precondition, it has a postcondition, or it has a condition that under which it will give you a useful result. So convert modular is convert narrowing, except sometimes you get the wrong, except no precondition, and sometimes you get the wrong result. That's how we should see it today. With that, we can return to our interface for assignment and modify it for any type. If we do an assignment from non-like types, we end up with substitutability between the result and convert modular of the right-hand argument. So assignment always does convert modular. There is some condition under which you will get the right result, but sometimes you will get the wrong result. Going back to our list, we can now strike assignment off the list. You'd think that would be progress, but we have added 3 more things to the list, so no progress yet. The next bit, we'll make progress, because all of these operations are covered by the same line in the standard. They're described by this one sentence. The behavior of an expression of the form E1 up equals E2 is equivalent to E1 equals E1 up E2, except that E1 is evaluated only once. If you are trying to write specifications procedurally, except that is not your friend. Except that means do all of this stuff, get an answer, except no, you didn't do that stuff up at the top. Fortunately, this naturally falls out of our syntax for interfaces, because we are going to let the caller deal with evaluating the sub-expressions and only give an interface for the actual plus equals operation. So we don't have to worry about that. Here is the interface for plus equals, and all of the other combined assignment operators work the same way. What we're going to do is compute an expected result by doing the operation by doing the corresponding non-assignment operation and converting modular to the left-hand type. And then we are going to, as a postcondition, say that the result is substitutable for the expected result. Now, there is one weird trick that I did in this. I put the computation of the expected result in the prologue. It's the responsibility of the caller. And that's because there might be some precondition on the addition operation. When there's a precondition on the addition operator, the caller of this operator is responsible for meeting that precondition. So that's why I put the computation of the expected result before the implementation line. There is one other trick going on here. I pass the right-hand argument by value in order to avoid any problem with aliasing. If I didn't do that, I would have to use an if statement. There's one change I'm going to make with this. I said I wasn't going to be using very much substitutability in my postconditions directly. This is that spot where instead of claiming substitutability, I'm going to claim that things are equal. Of course, that is, I'm going to claim that the result of the equality operator would be true. And that means that indirectly, I am hitting the true side of that branch in the postcondition of equality, and that's giving us substitutability. So that's how you write the interface for plus equals. That's actually how you write the interface for all of these combined assignment operators. So we are done with them.
Why isn't discern B there?
Why isn't discern B?
Discern A, sorry. Discern A. Isn't A part of the discernible?
Did I not say that? Oops. Yeah, I missed that. Should have said discern A. Thank you. Okay. We do have a few things left down below that are modifying things. There's a bit of a problem here. We would like to talk about the expected result of increment, but we don't have a corresponding increment operator up above. So we'll invent one, and then we are done with this. Same deal, we will invent a way to get the previous integer and put it on the upper list, and we're done with that. These last two are just a little bit more complicated because remember, they're the ones that return two different results. They modify the parameter and they return a result. But that's not very complicated. We have an expectation of what the result will be, and we have an expectation of what the value of A will be, and we will claim equality for both at the end, and we're done with that. Same deal for minus minus. The expected value of the variable A afterwards is the previous value of the variable A read before the implementation. Done with that. And now we're not modifying any of our parameters anymore. There are no rights being transferred into any of these operations. Still a right being transferred out because each of these creates a result object. And now we come to the part of the talk that I call unpleasant mucking about with types. Here's our list of types. We don't like doing math in these types. For reasons that I couldn't really explain, we don't like doing math in any of the character types or in anything shorter than int unless it is int, or even anything the same size as int. Unless it is int or unsigned int, those are okay. So what do we do to avoid doing math in those types? We do integral promotion. There is a reasonably complicated algorithm for how do you promote an integer. So there's one way to do w char t, char 16t, and char 32t. There's a simpler way to promote everything else. We can more or less write that as code. I don't like this code. Made me write conditional t. I don't like conditional t. If I wanted to write Lisp, I would write Lisp. But this more or less gets the job done. Why do I say it more or less gets the job done? Gives the wrong answer for bit fields. Why? Because the type of a bit field is a lie. Promotion knows the truth and promotes according to the actual width of the bit field, not promoting according to the lie that is the type of a bit field. I believe this is something we could fix in the standard. It's not easy, and nobody wants to spend their time doing the work that it would take to fix this. There is one other problem. Underlying type cannot be applied to character types. It doesn't work. Is this an oversight in the definition of underlying type? I don't know. But it is specified to only work for enumerated types, even though the wide character types have an underlying type. So that's not too bad. The standard does specify how to get the underlying type of char 16t and char 32t. It doesn't specify how to get the underlying type of w char t. I know no direct way to ask what the underlying type of w char t is. It probably doesn't matter because it would be a really strange w char t that couldn't convert nicely to either a long or an unsigned long. But there is that one corner. Of course, in practice, we wouldn't write this code. In practice, we would write a much simpler thing. The promoted type is whatever plus returns. Unary plus is the promotion operator. So there is an indirect way to ask what the promoted type is. And with that, we can create a couple of concepts. A promoted integral type is an integral type that promotion doesn't mess with. And an unpromoted integral type is an integral type that promotion does mess with. With that, we can more or less write the interface for unary plus. Why can't we totally write the interface for unary plus? Because this would be the use of promoted type up at the top here would be recursive if we used that definition. We have to use something like the definition that didn't quite work in this one case. So this is what unary plus does. We figure out what the promoted type is. We convert to the promoted type a nice conversion every time. And that's going to be, we are going to claim that the result is equal to that expected result. Coming back to our list, we can take unary plus off the list. But we're going to go further. For essentially every parameter here, we are going to do the same thing if it has unpromoted type. So I'm using my concept here. This is only the interface for unpromoted unary minus. What do? We compute the expected result by applying unary minus to the promoted value. And that's how we deal with unpromoted types. So, all of the operations on the left, we now are down to, we only need to deal with promoted parameters only. We will still allow unpromoted parameters for our conversions because we needed them on unpromoted parameters before. That's not enough though. We're going to muck about with types some more because apparently we hate doing arithmetic where the types of a binary operation don't match. And to deal with that, we have the usual arithmetic conversions. And we can write a function that does the usual arithmetic conversions. If the types match, we'll just return a pair. That's easy. If the types don't match, we'll do something complicated. What is the complicated thing? Well, it starts off easy enough. We look at the kinds. We figure out what the kind of the left type is, what the kind of the right type is, and if one is bigger than the other, we convert the parameter of small kind to the type with big kind. That's if they're comparable, if they're greater, if they're less, that's easy. If they compare equal, we could convert either way. We'll have to break the tie. And they could be unordered, in which case we will have to do something unpleasant. So, the equal case. There is something called integer conversion rank. We can use it to break ties. It actually covers a wider area than this. It considers the width and all, but I saved it for last because there is no template here that tells us how things compare by integer conversion rank. So I made that up. You can't actually write this code in C++ today. But apart from that, and I should say, we mostly know how things compare. Long beats long beats int. Standard integral types beat extended integral types of the same width. A signed and unsigned integral type that correspond to each other are compare equal in rank. But what the standard doesn't give us any direct way to get at is the comparison between two extended integral types of the same width. We just don't know. So I made one up. But anyway, you break the tie, you do a nice conversion, done. Last case, unordered. What do? We convert modular to the corresponding unsigned type and then try again. So, silently get the wrong answer. This one is a serious problem. This one makes you silently get the wrong answer when you compare a negative signed number to an unsigned number. Sometimes. So, this is one reason you should turn on all of your warnings. They might save you. Yes, you will often, so if you fall into this case, you will find negative numbers comparing bigger than 0, which is just trouble. And it's not just comparisons, it messes up your other math too. So that's the hard way to do it. What do we do if you really wanted to write this function? You just say the usual arithmetic conversion type is whatever plus would return, and we make a pair of that by doing convert modular. That's the easy way to write this. Where is the one place you can't use the easy place to write this, the easy way to write this? If you're trying to define the interface for plus. So here is the interface for plus when the types differ, requires clause up at the top. What do? Usual arithmetic conversions, and then we add the converted ones which do match, so it's not so we're not doing a recursive function here. And that gives us the expected result. Done. With that, we can shuffle things about and say for most of our binary operations, we only now need to worry about matching promoted parameters. I should point out there's two binary operations where we don't do the usual arithmetic conversions, the shift operations. We leave them alone. That, in my judgment, was a good call. Honestly, in my judgment, the usual arithmetic conversions probably a mistake all the way around. But it would have been especially a mistake for those two, because the right hand is really an exponent and you don't want to mess with that. Okay. We are done with nasty mucking about with types, but we do have a few very simple preconditions for a couple of the operations. Let's get them out of the way. For a/b and a%b, if the second operand is 0, the behavior is undefined. Now, the behavior is undefined talks about the behavior. It sounds like a postcondition, because behavior is what you see after. Behavior is undefined is actually a precondition. This is freedom for the implementation. It is total freedom for the implementation, and you can't let your implementations have total freedom. So it is actually a precondition. This is a situation the caller needs to avoid. But that's easy enough. The more complicated one, if the quotient a/b is representable in the type of the result, there's something otherwise, the behavior is undefined for both slash and percent. So this, again, except for that complicated expression, precondition, or postcondition. The otherwise clause is a postcondition. What is this about? It's about the most negative number of assigned type. There are more negative numbers in assigned type than there are positive numbers. There's one more. And if you're at the most negative number, you can't negate it, and you can't divide it by -1. So this is saying that division can't fall into that case, and it's saying that percent, the remainder operator, you can't take that remainder even though the right answer is 0. Just a sort of random restriction there. Also, for the shift operands, behavior is undefined if the right operand is negative or greater than or equal to the width of the promoted left operand. That's fairly straightforward. So here they are in code. a/b, b can't be 0. a%b, b can't be 0, and we have to be able to compute the quotient. Shift, we have to be able to convert narrowing to bit size t and compare against that bit size t that is the width of the integer. So the convert narrowing takes care of anything that is way too big for bit size t and takes care of any negative values. and then the comparison takes care of the two large positive values. So, those are the easy ones. We are down to the hard parts now. And one of the big hard parts is this. If, during the evaluation of an expression, the result is not mathematically defined or not in the range of representable values for its type, the behavior is undefined. So again, undefined behavior, this is a precondition. But this is a wacky precondition. This is a precondition that is about the result of the operation. What the heck is that? And before I get into what the heck is that, I do want to say that there are two clauses that modify this, which is arithmetic for unsigned types is performed modulo 2 to the n. We will get to exactly what that means, but it means that you are not going to have the undefined behavior down here. And also left shift is performed modulo 2 to the n. We are also not going to get undefined behavior for left shift. So, random exceptions to the rules, unsigned types and left shift. So, this business about a postcondition that talks about the result of the operation. What's going on there? Well, let's look at our picture. We have some operation we wish to perform in an integral type. What this is talking about is converting those two values down to z and performing the operation in z. It's doing the conversion down to z, doing this operation, and when that clause is talking about the result of the operation, it's talking about the result of the operation in z, not the result of the operation you're doing. And what is it saying about that result? It's saying that if you can't lift it back up to your original type, you have undefined behavior. So what do we have in code? Here's the code for plus. The result in z is to get the result in z, we convert down to z and add the values in z. And then we are going to do a lift, and depending on whether the types are the type is signed or unsigned, we are going to do a convert narrowing, or we are going to do a convert modular and potentially get the wrong result. But that's how we do the math in z. We try to lift it back up one way or the other, and post-condition, the result is equal to the expected result. There's a problem with this. Problem is z is not a type, or not a C++ type anyway. It's maybe a type theory type. It's a colimit. So what do we do instead? What does this mean, like in real code that we can write? And I'm going to take advantage of a little category theory here. When we have a problem, a bit of arithmetic that we want to do here, and we have converted it down to z and figured out the answer, we can then take advantage of a fact about this particular colimit diagram. It has a neat property, which is that if we consider the types that keep going through the dot, dot, dots, any two types that are in the upper part of the diagram come together by nice conversions before you get to z. That makes this a filtered colimit diagram. And a filtered colimit has a really nice property. In a filtered colimit, any finitely presentable thing can be lifted. What do I mean by finitely presentable? Any finite computation is finitely presentable, and so lifts to somewhere in the diagram. there is some place in this diagram that we can lift the computation to, not necessarily all the way up to where we started, though. But that gets us away from z. There is some kind of integer that we could do the math with. And we're doing types today, so I'm going to create some more types. There's a template here, widening types. They are templated on an integer kind k, and they are not C++ integral types. They do not follow the rules for integral types. They break all of these nasty rules on the left that we have seen before. None of that stuff applies to the widening types. But we get three things from them. Widening k has integer kind k exactly. The widening operations will, in general, return something wider than their parameters. The exceptions for that would be convert narrowing and convert modular. Because of that, they aren't going to have any combined assignment operators. That wouldn't work. But the best thing they've got is operations that agree with z. If we want to know what the answer would be in z, we can compute it with the widening types. And how do we implement such a thing? Well, I'm going to invent mathematical operators on the integer kinds. I'm going to say, if I add two kinds together, I get a kind that is big enough to do any addition that came from those original kinds. So the particular way to do that for addition is we find the join of those two things, we find the first place where they meet, and we add 1 bit. And there are simple expressions that figure it out for all the other operations. We are saved a little bit on the left shift by the fact that there was a limitation on how far we can left shift. So, left shift can only add, if you start with n bits, it can only add n minus 1 bits to your integer. And with that, I'm going to say we have addition for widening integers. Gives us if I add a widening AK to a widening BK, I get widening AK plus BK. And using that, I can't quite use it yet. So what do I need to use it before I can use it? I need two functions, toWidening and fromWidening. And the only thing to know about these is that they invert each other. That is, there's a postcondition on toWidening that if I did a fromWidening on it, I would get back the original value. And there's a postcondition on fromWidening that tells us if I did toWidening, I would get back the original value. It's a bijection. But this is no good. This is recursive. Recursive interfaces are bad. If you want to do a recursion, you should do it through an implementation. Recursing between interfaces without going through an implementation is bad. So, how do we break the recursion? A fairly simple trick. Here we have toWidening, the interface for toWidening depends on fromWidening, the interface for fromWidening depends on toWidening, but what we'll do is invent two more functions, primitive toWidening and primitive fromWidening, and we will let both toWidening and fromWidening have a dependency on both of the primitive versions. And the code that we want for that is this. toWidening returns the same result as primitive toWidening. That's a postcondition of toWidening. It is also inverted by primitive fromWidening. FromWidening returns the same result as primitive fromWidening, and it is inverted by primitive toWidening. put all of that together, you can only have a bijection. But the interfaces are not recursive. I should say this trick, I thought, was just a programming trick to get rid of recursion. It shows up in the Principia Mathematica. This is what the axiom of reducibility is used for in the Principia Mathematica. It says there are two different things that are, that are going to get, it's an axiom that says there are two different things that are going to give the same result, but they're different things, and that avoids a recursion. Having said that, we can return to our version of addition that converted to z, and making it a little more complicated, instead convert to a widening type. We compute the wide result by converting to widening and doing the operation, which may make it still wider than it was before. We figure out what kind we need to lift to, and we are going to do a lift in the widening types. We're going to use convert narrowing sometimes, we're going to use convert modular sometimes, because that's how the standard was written. And then our expected result is converting the lifted result back to a C++ integral type using from widening. And all of that in the prologue. So really, the precondition here, that the hard precondition, has been subsumed down to the call to convert widening there, or yes, convert narrowing on the widening type. And with that, instead of those types, we can get down to types that aren't C++ integral types at all. I am going to follow my earlier advice and not convert bit size t to the widening type. We're going to convert to bit size t for shifts on the right operand. That's just much nicer. So now we have widening math. We have to figure out what the interfaces for the widening math are. What do they look like? Well, this is the line in the standard that tells us what the interface for the widening math is in C++. The result of the binary plus operator is the sum of the operands. And the other operations have text like this. Man, the operator star, even worse, because it just says that it indicates multiplication, not anything about the actual result. But anyway, we get the idea. We are humans. We can read this text even if it is really an abdication of specification rather than an actual specification. What does this mean for the interface? Well, I'll show you the interface for widening plus. And from now on, I'm going to stick to plus because all the others are pretty similar. And I only have so much time. So what is the interface for widening plus? This is the interface. We have to extend, the caller has to extend immunities for A and B. A and B are the discernible input. The caller gets a right of stability to the result. The result is the discernible output, and nothing. I'm hiding something, of course. I even left a blank down there because I'm hiding something. I'm hiding it for a good reason. I'm hiding it because the thing that would go there would be all full of nasty if statements. And I don't want to put nasty if statements in an interface that is called through a long chain of things from simple addition. I don't want to inject if statements into every bit of code that adds. So I'm going to use a trick to avoid doing that, to hide the if statements from that code. I'm going to say, for a postcondition about the value of the result, call this function. And reference add axiom will tell us something extra about the result if we call it. So that means I have to show you the interface for reference add axiom. What does that look like? This is an axiom. An axiom is a kind of interface. It's a special kind of interface where we use the word posit before the implementation, and that has a special meaning. This means that the implementation here doesn't actually exist. There is no implementation. It's saying if you meet the preconditions, the postconditions will follow for reasons that are not expressed in C++. It's an axiom. It's a fundamental thing. You want to be careful about doing this sort of thing, of course, because you can get any postconditions shown by using an axiom. But here we have a very simple postcondition. We're going to say, if you can compute the sum, you can also compute reference add with carry, which is a function I will show you in a moment, and that function will produce the same result. So this is, again, one of those axiom of reducibility situations. I'm just doing an indirection to hide things that are complicated behind an extra step. And of course, there is some reason why plus is going to return the same thing as reference add with carry. But that's just because we require compilers to do a plus that is going to produce this same result. But the reason is outside what we can express in the language. So, what is reference add with carry? Well, some of you may have seen this before, but here we go. Suppose you have two numbers that you want to add, and you have a 1-bit carry. What do? We split them into a high digit and a low digit. We add the low digits and the carry to produce a 2-digit result. We split that into a 1-bit high digit and a low digit. We use that as the carry when we add the high digits. That produces a result. We join those together to give us the result of the original addition. That is what we want to express with reference add with carry, because this is what the standard was saying when it said the sum of the operands. It means the thing you learned in school was sum. And this is why all of us could look at that simple sentence and know what it meant, because we spent a bunch of time in school learning this algorithm. What is this in code? Well, here's some code. We split AB into A and B. We split CD into C and D. We add with carry. We split the bits. We add with carry again. We join the bits. That's the code. It's just what I said. It's not all that complicated. It's a wodge of code. It does, of course, have a big if const spur saying that we only do this in some cases. We can't split things into high bits and low bits if there's only 1 bit or if there's 0 bits. Also, we don't want to split both of them if one of them is much wider than the other. My favorite choice for the low width algorithm is to pick the largest power of 2 less than the width of the integer. That gives you a nice splitting. You get your binary reduction, but you keep reusing things that are powers of 2. So that gives you, that's the one I'm imagining behind this. But anyway, that's the case for two things of approximately the same width. I won't show you the cases for one thing much wider than the other, but there are important cases where you just can't split because you're doing 1-bit integers or you're doing 0-bit integers. What happens then? Well, here is the unsigned 1-bit integer case. This is the big wodge of if statements I wanted to save the world from. This is code I really don't expect you to read all of. I can see that some of you are trying to read all of it. It's just if statements three levels deep. It's just doing this. There are 8 paths through this code because it's if statements 3 levels deep. And in each case, it joins 2 bits together to make a 2-bit result. There are 8 paths. There are only 4 possible results. Some of the paths, there are paths that produce the same result. So that's how you add 1-bit integers. You run through this algorithm and you pick a result. And with that, we have gotten rid of all of that stuff. And the only things we have left are bit to bool, bool to bit. That's just a bijection. We know how to do a bijection. Bit to bool, that is taking bool to unsigned widening 1-bit integers. And you need a negative a signed version of that, taking bool to a signed 1-bit integer. And then we have split bits and join bits, which are just, treating numbers as bit strings. Split bits and join bits not exactly inverting each other. Sometimes they do, but sometimes the join doesn't happen quite on the split that you would choose. So maybe you want to do split at an arbitrary point, give it an extra template argument of bit size t. But that's not very complicated. It gets boring after this. I'm not going to show you all that stuff because I want to show you something more interesting. And the thing I want to show you that's more interesting is what you can do once you have all of this. The answer is we can use this to prove theorems. What's a theorem? Here's what a theorem looks like. It looks a lot like an axiom. There's one word that makes this not an axiom. We used claim instead of posit. We are not going to assume that the postconditions hold. We are going to say there is some implementation of the theorem, and the implementation we can think of as a bunch of assertions that lead us from the preconditions to the postconditions without changing anything. The implementation is dispensable code. We don't have to call it in, we don't have to include it in our executable the same way we don't have to include an assertion or an interface in our executable. It's something that we can include in our executable if we think the theorem might not be true. It would check the reasoning. But if we don't feel like checking the reasoning, we can just compile it out. Anyway, the implementation basically gets us logically from the preconditions to the postconditions. And what is this particular theorem says? Well, title, addition is commutative, should give you a good clue. What it's saying is that if I do 2 add with carries, and I reverse A and B in the second one, I get a substitutable result. That is, it doesn't matter what order A and B are in, I get the same answer. That's what this theorem is saying. So, precondition, you have to be able to add in both ways round. Postcondition, the 2 results are going to be substitutable for each other. So, how does the proof go? Well, first step in the proof, we call the reference add axiom. What does this do? It visibly does all of a reference addition, and it says that add with carry produced the same result as reference add with carry. So why do I say it's visible? The interface for Reference Add Axiom, which only has an interface, it's an axiom, no implementation, the interface called an inline function that was not hidden behind an interface. So that whole inline function is part of the neighborhood of our proof. What is the neighborhood of our proof? It's the interface to the proof, the implementation for the proof. It's every inline function called from any of that unless it's hidden behind an interface. And it's all interfaces that are called from any of that. So that's the neighborhood of our proof. That is the hunk of code that we look at to see whether our proof works. And so here we have injected all of that stuff into our neighborhood, an entire reference addition, just by making this one call. What do we do next? We're actually going to repeat some of the reference addition so that we can get at its intermediate results. We're going to do the split, and then we're going to take those low digits and apply addition is commutative to them. We're going to say it didn't matter which order B and D were in when we added the low digits. We could add them in either direction and get the same result. So we call addition is commutative, not recursive, by the way. We are calling a different specialization of the same template. What do we do next? We'll do some more things here to figure out what the high bit addition was. Again, repeating stuff from the reference addition that we did before. And we will do the same thing to the high bit addition. It doesn't matter what order A and C are in, we get the same result for the high bits. And then we are done with those intermediate results. We can throw them away. And final step, we're going to call reference add axiom with the parameters reversed. So what is this? It's showing us how to add these two numbers with the parameters reversed. But the thing you'll notice, if you actually follow the code through the neighborhoods, every step of this reference addition either repeats a step of the first reference addition, or it repeats something in the interface for addition is commutative that was shown substitutable for a step in the earlier reference addition. That is, everything here is either repeating the first reference addition, or it is substitutable for something in the first reference addition. So just by following this code through its entire neighborhood, starting with its interface and ending with the postconditions of its interface, and running through all the interfaces it calls and the inline function reference add with carry. Just by following through all of that and keeping track of what is stable, of what is substitutable, and what is repeating something, we can see that these two reference additions are going to produce substitutable results. And because we know the reference additions produce the same result as the produce results substitutable for the real additions, the real additions also must have substitutable results. That's the proof. What is the code for the proof? It is exactly what I said. Here we go. Reference add axiom, split bits, addition is commutative. Add with carry, split bits, addition is commutative, reference add axiom. That's the whole thing. And I want to stop here and say, in my experience, people will look at something like this and say, that's a bunch of procedural code. And because they say they think that's a bunch of procedural code, they will think it follows that that is not a mathematical proof. This is both procedural code and a mathematical proof. in this one case. This is the case where we do split the bits on both, and there are the other cases where you only split the bits on one of the parameters. There are the various cases for not splitting things at all because they only have 0 or 1 bits. But this is the proof in this case, if the if const expr holds. I'm going to leave that up there for just a few more seconds so you can read it carefully if you like. Okay, that's enough. I do want to show you what we do if we can't split things because they're too small. So first thing we're going to do is call the reference addition axiom again. And that will do, that will inject all of these branches into our neighborhood. It's like we're breaking into 8 different cases. And then we are going to call the reference add axiom with the parameters reversed. And that also breaks into 8 different cases. But the cases line up. Every branch in the second call is repeating a branch from the first call. It's going to go the same direction. We're not repeating them in the same order, so we won't take the same path as before. But every branch in the second call goes the same way as some branch in the first call, because what are we doing? We're asking, what are the, is the first parameter 0 or 1? Is the second parameter 0 or 1? Is the carry 0 or 1? We're asking the same questions. We're getting the same answers. We're branching in the same direction, just with our branches reordered. And it just so happens that we chose the answers that we were given on those 2 branches in every case to be the same. We used the same expression to figure out what 1 plus 0 was as to figure out what 0 plus 1 was. And because of that, it's going to be substitutable in every case. We are repeating the same expression, so it will be substitutable. And what does the code for this look like? It just looks like this. It is very simple. It's saying if you look through the reference addition algorithm, it will be obvious that the 2 reference additions produced the same result. And therefore, the 2 real add with carry calls produce substitutable results. So that's the proof in the easy 1-bit case. And that is most of what I have to say today. There is one more thing I want to add, which brings us back to this colimit diagram, which is really at the heart of how we think integer math works. It's very easy looking at something like this, and particularly brought up the way I was, and probably many of you were, to think z here. Z is the real thing. Those other things, those are approximations to z. They are somehow lesser. To borrow a metaphor, those are shadows cast on the wall of the cave by the light shone by z. That is a pernicious way of thinking. That sort of thinking can mess you up. If you want to write a good specification for something that is real, you need to write it in terms of these things. This is what's real. This is what's in the world with us. These things are what our computers compute with. So if you want a good specification, write it in terms of the stuff that's really real. On that note, thank you for listening. Are there any questions?
Okay. On the commutative of the A and the B and the L with the carry, don't you actually have to prove that you can communicate the carry bit also?
So repeating the question, did I skip a little step so showing that the carry bit was being repeated? And so I did actually skip one thing, which is I showed you I never showed you the interface for true add with carry. I only showed you reference add with carry. So yes, I should have put one more interface in there. It was kind of running out of time, so I didn't think I would end even this early, and it's not very early. So yes, there should have been an interface for add with carry and an axiom that says that add with carry also produces the same result as reference add with carry, but it supplies a value for that defaulted carry argument. I hope that answers your question. Yes?
Would you say that with this technique you can basically obtain all the constructive proofs that there are?
So,
Rule out existing proofs and non-constructive proofs?
So the question is, can we do any constructive proof with this technique? My answer is yes, but. I showed you the easy example here. Proofs that have loops in them are a little harder. They're only a little harder. So, I didn't think I could cram, and they don't really show up in this case. The arithmetic proofs, you don't need loops for that. You're just splitting things up and shoving them together. So if you have a problem that has loops in it, I know some of you are thinking halting problem. Halting problem is not our problem. You can look that up on the internet and see me explaining why. The halting problem is not our problem. If there are loops, there is an extra thing to consider, making sure that you have shown that your loops will end. And yes, we can show that loops end. We are very used to showing that loops end. It's just that the halting problem has been confused for the inability to show that loops end. Yeah, you can do it. There's a little more complication if there are loops involved. Anybody else? Oh, I think you were first.
I noticed a ternary in your convert, since only one branch is possible depending on the inputs. That's not like a true branch, but I was wondering if there were other, if ternaries were in some way fundamentally different from the if result of your equality.
Did I actually write that with a question mark colon?
Yeah.
Oh, if I was being good, I would have written it with an if const expr. I think in every case it was an if const expr that should have gone there. So yeah, I don't want to put runtime branches. If const expr is not a problem because you always know which way it goes. That's not a complication.
That clarifies for me. Thank you.
Yes.
So one of the reasons why Russell's book was so hard to read was that they didn't have computers at the time, and doing all of this stuff on paper is very tedious. So did you actually have an implementation that checks this, or did you only do it all?
So I have done partial implement. Oh, the question is, do I have an implementation that checks this stuff? I've done partial implementations. They're hacky. One day I would like to do, or have done for me, if any of you want to do the work, I would love to have an implementation that's maybe based on Clang and does all of this nicely. But it is a lot of work just to do the theory behind it. And so, yes, a lot of this is proof-wise slideware. I did make sure that a whole lot of this stuff does compile modulo the changes I've made to the language. Yes?
For the add with carry, was there a reason that you used just the if tree instead of using like the logical operations to calculate the add, or the sum of the carry bits?
Okay, so the answer is for the add with carry, is there a reason I used a great big if thing instead of using logical operations? And there is an answer, but it's not a very satisfying answer. I wrote it with using logical operations first. And then I realized I had to present a great many more interfaces for you to all see the code, and the talk was running long. And if I wrote it with the big if statement, then I wouldn't have to do quite as many slides, and I would get to the end of the talk on time. In practice, yes, I would do that. There would still be if statements when you get down to how do the logical operations work. But this let me avoid talking about the reference logical operations. Yes. Yeah, you.
You built the, I don't know how to describe it, the system on top of binary operators. Right? I mean, the operators that has no side effect.
Yes, I reduced to the no side effect.
Yes, but in the end, you'll find that all those machineries are operational.
Yes.
Would that be simpler if reverse this?
Would it be simpler to do the operations, to do operations without side effects in terms of the operation, the combined assignments that don't have side effects? Well, my answer is no, but for a weird reason about the terminology. Yes, we talk about those combined assignments as having side effects, and the simple operations, plain plus instead of plus equal, not having side effects. That I hate that term. I think that the way we use the word side effect in C++ is pretty misleading. There is a change that happens when you call ordinary plus. The change is a new object is created, and the caller gets that write to stability to the result object. It is a change. It's not, in C++ standard terms, a side effect, but it is a change in the world. So I find it more convenient to work with the 3-value version than the 2-value version. There's going to be a change in the world anyway, so I might as well just make it the one that separates things out, and I don't have to do the extra conversion at the end. Particularly for the widening types, where the result of the widening addition has a different width than the parameters. Does that help? Yeah. Yes.
Regarding the implementation, is there a specific reason, if you had time, infinite time to do it, would there be a specific reason why you would want to do that in C++ rather than in Theorem proper, for instance?
So
something, or is it just a personal preference?
So the question is, if I understand it, why C++? Is that a fair? Yeah.
Specifically, is it personal preference, or do you think it adds?
So C++ adds something personal for me, which is that I do this work with C++ not because it wouldn't be easier in another language, particularly a newer, less wordy language, but because it is harder in C++. I would love to see this in other languages too, but I have looked at what people have done in very new languages trying to do stuff like this. And there's a history here. There's, many people have gone before. Probably the first one I encountered was David Grease, and that was back in the 80s. He had a language, and it was a language that nobody used, but it did try to do some of this stuff. And man, what was the... Yeah, I think the name of the language is Alfred. But anyway, The Science of Computer Programming, that was the book. Anyway, it's very easy to, in my estimation of how people who've gone before me have found it, it seems to be very easy to fall down a rabbit hole of not paying attention to how programming works in the real world. And C++ keeps me honest.
I want to use C++, but maybe you misunderstood my question. It's not about doing that for another language. My question is, if you had to implement your proof system, why would you choose to implement that proof system for C++ in C++ rather than the proof system for C++ in Code or Agda or...
So the question is, would I do the proof system for C++? Would I express the proofs in C++? And yes, I think that it is important to be able to express proofs in the language that you are using. I want proofs in the future to be a standard part of our programming practice. And when we write programs, we use one language. I don't want to say, I'm going to write the program and then I'm going to write the proof separately. I want to combine them into a single source. So I want, in the future, to have computer languages in which we just bring people up from their first programming courses as knowing how to write proofs that their programs won't have undefined behavior. Yes?
I see the technique is very centric on binary operators. Do you have a problem to turn these to, let's say, showing that plus and times are distributed, for example? It's the same technique.
Yeah. So distributive is showing distributivity. Basically, I mean, you'd have to think through the proof a bit, but it is basically the same technique. You split it, you do the distributivity on the parts. That's pretty easy. And most of those basic mathematical facts will work out that way. There is a further step that you can't do with distributivity that I would want to do with plus. It would be nice to put into the interface of plus that plus is commutative. If you just you could just put into the interface a call to the theorem, and then nobody else has to call the theorem. Every time they add things, it will just be in their neighborhood that it's commutative. Not quite that easy, because that would be recursive, but you can do that same primitive trick to break the recursion. And you would say, okay, I'm giving you the same results as primitive plus, and primitive plus is commutative, and that would work. You can't do that with something like distributivity or associativity because they have too many parameters. Those are 3-parameter theorems, but you only have 2 parameters in any given interface for these operations.
Second short question. Is there any hope that this could work for proving stuff on real numbers?
Okay.
Because if it is, it looks like you
So,
idealize case in a single way, but to get to the real, there's so many ways to get
okay. So I think I'm over time, but I am going to answer that question in violation of the rules. Is there any hope for doing this for real numbers? There is. Real numbers are weird. Modular arithmetic done right is also weird in the same way. That diagram with the z being a colimit turn that upside down, the arrows still go down, but we follow the back of the arrow back to R when we're doing real numbers. The nice arrows are actually loss of precision arrows for this diagram, and the real numbers are a limit, not a co-limit, and finite co-presentability is much more difficult. But and the same thing happens for modular arithmetic. You end up at the p-adics. So yeah, that's whole another lecture material individually. Okay, I think we're out of time, so I'm going to cut it off there, and I'll be out at the coffee area soon.